Today is my eccentric load on the welded joint. This class is the load on the welded joint due to eccentric load. From the first figure, there are one plate. This is plate 1 and this is plate 2. Plate 2, which is joined together by the parallel fillet weld along the parallel of the both side of the equal length of the fillet. Here applying the force of P from the center of gravity, which is eccentric length, which is denoted by E, and from the G center of gravity, and load is applied distance from E, which is load is the P Newton, hard distance from E. Now the second figure, figure 1, figure B, 1B, which is shows that the M is the couple. M is known as couple, C-O-U-P-L-E, couple, which is the value is force into eccentric distance. This value is balancing the force, where the applying the force P from the eccentric distance E, and balancing the force and put the force P at a point of the center of gravity G. Therefore, this figure is partially divided into two parts. First part is the load by the P and another part is the load by the couple. And P is applied due to the direct stress, which is known as the primary stress. Primary stress. This is shear stress, which value is tau equal to P by A. A is the area of parallel fillet weld. From figure 1A, this is denoted, writing here the W1 and W2. This is denote the parallel fillet weld 1 and parallel fillet weld 2. Now, the making the equating of the equations in which the stresses are working on the eccentric load. Now, the area of a throat area is A is denote the throat area of the all welds, and tau 1, this is tau 1 is the P by A area of the throat, which is distributed equally and uniformly distributed over the area. W1 and W2 is the fillet weld throat, and tau is the P by A. Now the first calculation is from the figure 2A. The tau is the straight uniformly distributed on the upward straight lines, as shown is here, and couple M, which is apply on at the center of gravity point, which will rotate the second plate B, which is parallel welded joint from the plate A. Therefore, when the couple M is to try to rotate by the torque moment, therefore tau 2 is the secondary shear stresses is applied on the anti-clock moment, which is balancing the couple. Therefore, first figure and second figure is combined together, and resultant is the tau 1 and tau 2, and goes to the tau. Finally, we get the shear stress tau, which is the tau 1 and tau 2. Therefore, tau 2 is here from the figure 2b. Tau 2 is the secondary shear stresses. And in which formula we got the secondary shear stresses? Then it will get the torque equation M by I, torque equation T by IP, Fs by R, and G theta by L. And applying this equation, we get the secondary shear stresses. Therefore, secondary shear stress tau 2 equal to T into R by J, where J is the polar moment of inertia IP and tau is here M, which is the torque moment M, into R, which is the radius, which is the maximum distance of the radius. This is the minimum distance, which is less value of the turning moment. Therefore, we apply the maximum distance, which is the center of the fillet weld W1, which is area. A is denoted the area. This value is R1. R is the maximum radius, which is applying the maximum torque for the tearing the fillet weld. Now the again next figure is W1 is the weld where the throat thickness is T and L is the throat length. Therefore, G is the center of gravity of this figure and the G1, and G is the total center of gravity of the weld. Now we get the calculation from the figure. First apply the Ixx. Ixx equal to B d cube divided 12. Then B is here L T cube divided 12, and about y axis Iyy equal to dB cube divided 12. Therefore, D is the T, B is the L, B cube divided 12. Here, T is very less than L. Therefore, Ixx is neglected. Then we got Jg1 equal to Ixx plus Iyy equal to Iyy only, which value is TL cube divided 12. Again, Jg1 equal to T into L square divide 12. T into L is the area, which is the rectangular section. Then T into L equal to area. Then area into L square divide 12. This is the Jg1. From the center of gravity G, applying parallel axis theorem, of moment of inertia Mi, Jg equal to Jg1 plus area into r1 square. This value, area into r1 square. Jg is equal to area into r1 square. We put Jg1 area into L square by 12 plus area into R1 square. Therefore, Jg equal to area, small bracket we have taken L square by 12 plus R1 square, where number of welds are present, then polar moments of inertia is polar moments of inertia are J1, J2, J3, both are dotted points. Then it will J1, J2, J3, J4 and continue etc. And finally the polar moment of inertia J equal to summation of the J1, J2, J3 and continue etc. Thank you.